And here we are now to talk about bivariate distributions in the form of continuous distributions. This is so exciting today, you won't be able to stand it. Okay, so what we're really going to talk about is the idea that x, and y can vary at the same time, and they can vary continuously. So it isn't like we're looking at little particular chunks of information for, let's say, we have 0 as our first part that is a good part and 0 as our second part that is a good part, and so we've got that sort of discrete distribution. Here we can vary continuously, and so you can see by the rise here of this probability density function, that's sort of like the z, the height above this xy axis, is what the value of that probability density function is. And what this is telling you is right in the middle where it peaks up here, that's where it's most probable that you'll have your result, and that's with a mean of certain values. And we're going to talk about all of these things in more detail. In essence, you can say that the joint probability density function in any particular place can be calculated by simply, well, taking a chunk of the volume underneath that tent in those particular areas, and that will give you the joint probability density function between those values. And I'm going to show you, we're going to work through some particular problems that will illustrate these ideas. In much the same way, the marginal probability density functions are given by, well, let's see, if we add up all of the values for the function over the y, and then likewise over the x, we'll find what the marginal probability density functions are. So I do like this particular drawing because I think it gives a nice illustration of the difference between marginal and conditional probability densities. So if you look here, pretend this is kind of like a big hill, just like we saw earlier with that peaked function. So if you took this hill and you looked at it from the side, notice how if you could take every value here and smoosh it flat onto the x-axis, all you would see would be this distribution right here. By the same token, if you took every single value and smooshed it flat onto the y-axis, what you'd see is what you've got here with this normal distribution, which has its own mean and its own standard deviation. So each of these means, this is the x, this is if you smoosh it flat on the y. By smooshing it flat on the y-axis, I really mean add up all of these different values, and that's what you got here, the marginal probability. Likewise, add them all up from this perspective, and that's what you've got on the x-axis, the marginal probability by adding up all the y's at that x value. For a conditional probability, you just set your x, for example, at a particular value, and then you see what the y values are at each of these locations at that particular given x. And this indeed is your conditional probability density for a y, given that you've got x at some particular value. So I like this chart because it shows a lot of the different ideas as far as joint and marginal and conditional, and what each of them means and how they relate to one another. So the joint probability density function is indeed a probability density function. So it's got to be greater than 0. You can't have a probability that's or less than 0 for all x, y. And that volume has got to sum up to 1. Now let's take an example here. This one says we've got a process, any process basically for producing an industrial chemical will yield a product that has impurities. So for a randomly selected sample of a particular chemical, we're going to let those random variables x be the proportion of all the impurities in the sample, and y will be the proportion of type 1 impurities among all impurities found in the sample. So we've got a x and we've got a y. After we've done some snooping around, we find that our probability density function as a function of both of those variables is given by this equation, where 0 is less than x less than equal to actually 1, and 0 is less than or equal to y is less than or equal to 1, and 0 elsewhere. So we're supposed to determine the probability that x is less than 0.5 and y ranges between those values shown. So this is actually pretty simple. All we're going to do is integrate, well, let's see, x is less than 0.5, but we know that it ranges from 0 to 1. So we're going to say it goes from 0 to 0.5, and that's our function right here, 2, 1 minus x dx. And then it also ranges from, let's see, they want to know 0.4 to 0.7 dy. So what we're doing is this function right here indicates the height above the xy axis. This dx and dy, that's like a little dx and a little dy, and we're actually taking that and we're summing that up over all, between the limits that we've got right there. So it's a lot of little dx's and dy's that we're summing up between the limits that are outlined here. Now you may say, I have no idea how to do this kind of integral, but it's really pretty easy. All you have to do is, first off, we're going to do the dx part. So I'm going to take it like this. Now, if I had happened to have a y in here, I'm just going to dot this in, but I'm going to erase it. If I had happened to have a y, I would have treated it just as if it was like a number, like 2 or 5 or something like that. In other words, I would have just pretty much left it alone, okay? But we'll see examples of that later on. Okay, so we're going to take this blue part right here and we're going to integrate it. So first off, we know it's going to be 2x minus, and then we've got the 2 on the outside, so it's going to be 2x squared over 2. Oh, well, that cancels right there. And we'll evaluate it from 0.5, between 0 and 0.5. So I'm just doing this part on the inside, and that should end up being 2 times 0.5 minus, let's see, 0.5 squared, right? And that's evaluating, we're going to stick 0.5 in here and 0.5 in here, and that's what we get. Now if you wanted to, you can stick the 0 in here and the 0 in here, and you can subtract it, but I guarantee you it'll just end up being 0, so we won't bother with that. So anyway, 2 times 0.5 minus 0.5 squared is equal to 0.75. So now we're going to continue. We will turn to blue. This part right here, turn to green. 0.75 is this. And now we'll say 0.4, 0.7 dy. Oh, okay. So now we're going to go, this is actually going to be 0.75 y, right? That's the integration. Evaluated between 0.7, oops, and 0.4. So that's just 0.75 times 0.03, which turns out to be 0.225. And by golly, that's exactly what we've got right there. So when we determine the probability that x is less than 0.5 and y ranges between those values right there at the same time, that is the probability right there. Now, if you'll recall, the conditional probability function said that given a particular value of y, what's the probability of finding some x can be calculated using this equation. Remember, it's sort of like saying this in our denominator is the whole world, and we're trying to calculate the probability of some set example or some set value of x and y. So this concept is also going to apply to continuous bivariate distributions. So what we do is use it to calculate conditional probabilities. So sometimes when we're trying to calculate a conditional probability like this, we can substitute in this value right here. And we'll see an example of that in some of the problems to come. So now we have a problem to do. Let's suppose that we have x and y and they're independent random variables with probability densities. And well, in essence, what we're really looking to find is just the expected value of these guys. Z is equal to x, y. So we can say then that EZ is equal to x, y. So that's going to be, now remember that idea of expected value is x times f of x, right? And you integrate it, or you add it all up. So we're going to take that same idea here and we're going to say, well, let's see, we need to have, let's see, this is 8 times x to the third, and then h of y is 2y. So I've got g of x, h of y, and then that's going to be multiplied by x, y. So we're taking the function itself, or the distribution function, probability density function, times x, y, and then we're going to sum it up between dx goes between 2 and infinity, and dy goes between 0 and 1. Okay, because we're just finding expected values, so we've got to multiply the density functions times the values themselves and integrate over the whole shebang. So here we go. Okay, 8 times 2 is 16. And then when we simplify and work things out, you can see y times y is going to be y squared. And we've got an x upstairs and an x to the third downstairs. So that's going to leave us an x to the second downstairs. And then we've got dx, dy, integrating 2 to infinity, 0 to 1. Okay, so now we have that. Now, let's take this as 16, integrating 0 to 1, 2 to infinity, y squared x minus 2, dx dy. I like to write it, whoops, that's minus 2. And so then we're going to integrate just with the x. So remember, just hold this constant, don't mess with it. We're going to keep it there as y squared, and this is going to be x to the minus 1 all over minus 1, right? And let's see, we've still got our 16 out in front, right? So got that there, 16, and we'll take, so this is 0 to 1, and for this part right here we're going to integrate it from the limits, or we've already integrated, but now we need to work the limits. So in other words, we want to work out this number right here, and we're going to do that. We'll have, let's see, this part right here, this is going to become, well, I'm going to put everything that's still outside, 16, 0 to 1, and then that part right there is, when we plug in this first limit, it's going to go x to the minus infinity. Well, that just goes away. Here we have a minus 1. This is the subtraction part, so we're going to have minus 1, which is a plus. So we'll be left with y squared 2 to the minus 1, and oops, minus 1, and then dy. Okay, so now we've got this step, and then next we'll go, let's see, it's going to be 16 over 2, because look, this part just becomes 1 over 2, so that's what I brought out here. And then we've got 0 to 1, y, let's see, y squared dy is equal to 8, and now I'm going to do the integration. Y to the third over 3, evaluated from 1 to 0, or 0 to 1. So it ends up being 8/3. Check. That's the expected value of x times y. Okay, for this next one, we are going to have our hospital period in days for a certain random kidney disorder is a random variable. Y is equal to x plus 4, where x is the density function. And we can say that the average number of days that a person is hospitalized for treatment for this disorder would just be given by the expected value of y, right? And that's actually going to be the same as the expected value of x plus 4. So all we have to do then is do our usual, remember it's x times f of x, integrated over the whole shebang. So we'll do exactly that. We're going to say, if we take, well, let's see, this function right here is 32 over x plus 4 to the third. So we've got that, and if we, that's our sort of like our f of x right there. Our x part would just be what? X plus 4, right from here. So there you go, it's x plus 4, and then times dx, and here we go, it's, we're going to integrate it between now and infinity, right? So what we're actually looking for, these two nicely cancel out, so it's going to be 32 over x plus 4 squared dx, integrating from 0 to infinity, 0 to infinity, 32 x plus 4 minus 2 dx, and that becomes 32 x plus 4 minus 1 over minus 1, and there's nothing leading the x, so we're good. And take that between infinity and 0. So in other words, we have minus 32 over x plus 4 taken from infinity and 0. So that becomes, let's see, well, we plug in the infinity to begin with, and that blows this thing to 0. And so that leaves us only with plus 32. We're plugging in the 0 right there, so it's going to be plus 32 over 4, which is 8 days. And that's going to be our average number of days that a person's hospitalized. Okay, so now we want to find, we're supposing the x and y, we're going back to some discrete examples, have the following joint probability function. Find the expected value of this particular g, function, which consists of x times y squared. So to do that, we can, let's see, the expected value of any function g x y is going to be, well, in this case, it's going to be e xy squared, and that is going to be just the summation over all the x's and all the y's of xy squared, right, times the probability density function at that particular location. So then we proceed to do that. We go, let's see, 2, if x is 2 and y is 1, right, then we're going to have 2 times 1 squared times the probability density function right there, which is 0.1, plus 2 times 3 squared, right, times 0.2, that's what we've got right there, plus 2 times 5 squared times 0.1, plus 4 times 1 squared, 0.15. I think you can see the pattern here. 4 times 3 squared, 0.3. And last but not least, we've got 4 times 5 squared times 0.15. And that is all equal to 35.2. And that is the value we've been looking for. So we've got that. Now, for part B, they say find the mean of x's and the mean of the y. So our mu x is going to be equal to e the x, and we calculate it in our usual way using the marginal probabilities. It's going to be 2 times 0.4. Right, so where did we get that 0.4 from? We just added up all the different values here, and that's 0.4. So that's sort of like smooshing them all, adding them all up. Those are the densities for the marginal distribution for y. X is equal to 2, and then plus, we've got 4, and so likewise we're going to add those all up, and that's maybe 0.6 is equal to 3.20, and for the mean of the y is going to be 1 times 0.25, right? So we're just summing those marginal probabilities. 3 times 0.5 plus 5 times 0.25. And all of that becomes 3.0. So we're done. Now for this particular problem, we're going to suppose that x and y are independent variables, and we're supposed to find these expected values. Now, this is the same table we've just worked with, and we found that the expected value of x was 3.2 and of y was 3.0. So we can now say that the expected value of 2x minus 3y, which is what they're looking for right there, is just going to be equal to, now remember, it's independent random variables, so we can play this trick. We could say this is just the same as 2 times ex, well, I should do this so I get this little 2ex minus 3 times ey. So that is just 2, remember from right up here, 2 times 3.2 minus 3 times 3.0. And so all of that is minus 2.60. And so that's our expected value for this equation, minus 2.60. Okay, well that's easy enough. That's part A. And part B, we want to find the expected value of x times y. So we know because it's independent, we can actually say it's ex times expected value of y. And so that's just 3.2 times 3.0, which is 9.6. Check. Not too bad. Now, last but not least, if a random variable x is defined such that we've got an expected value is 10, and this expected value is 6, find the mean and the standard deviation. This is just such a nice problem because it looks so boggling to begin with, but it's actually very straightforward. Let's say we've got this x minus 1 squared. So that's going to be x squared minus 2x plus 1 is equal to 10. Or at least the expected value of that, right? So what's the expected value of x squared? Well, it's the expected value of x squared, right? We can do each one of these independently. Watch. Okay, so this one is 2, expected value of x. Okay, now, what is the expected value of 1? Well, it's just a constant, so it's going to be actually 1 itself, right? So it's going to be plus 1 is equal to 10. So then it becomes expected value squared minus 2ex plus 1 is equal to 10. In other words, those two values, I'm going to take the 1 over the other side, all of that is equal to 9. Now, if we play the same game with this one, we're going to get a second equation. And that equation is ex squared minus 4x, or 4e to the x, is equal to 2. So, right, and the way we got that, we just said x minus 2 times x minus 2 is equal to x squared minus 4x plus 4, and we plugged that into our little expected equation, and then we rearranged everything and got the second equation. Now we have two equations with two unknowns, and that allows us to figure out precisely what we need to know. If you solve away, you'll find that ex is equal to 7 over 2, and ex squared is equal to 16. So with that knowledge, now remember, expected value is just the mean, and so that's 7 over 2. And then the variance is just going to be x squared minus e squared x. And so that's going to be 16 minus, did you hear my cat? Okay, 7 over 2 squared, and that all becomes 15 over 4 is equal to sigma squared. So we got our answer there. Here's our mean, and there's our variance. And that's all for today, folks.
Oh, son of a gun. You thought I was going to say son of a bitch, didn't you?